Okay, Professor Jim Schultz here for my Finance 13 students. I wanted to go ahead and shoot our first YouTube video of the online semester. Whenever I send you guys out problems to practice, I will always do two things. I will always send you the solutions to those problems like I've done, and then I will always do a YouTube video not going over each problem, only simply from a time standpoint, and some of the problems are very similar, so once you kind of know how to do one, you can probably figure out how to do another one. But I'll pick a couple that I think are really useful to understand really well, and we'll knock through those guys to see, to make sure you guys have a better understanding of what's going on. And so the two problems I'm going to go through in this video are going to be number 2 and number 8. I think these are really good problems to know how to do well, and especially in the case of number 2, there's kind of some components to this problem that obviously if we had class face-to-face, I would be able to share these with you, but since we don't, I thought, okay, I'll just kind of roll that information into this solution video for the problem. So number 2, if you look at number 2, if you look at the actual question, you have two parts. You have to find the inflation premium, and then you have to find what is the equilibrium interest rate on this Moore Corporation company. And actually, let's go down to part B first, about the equilibrium rate on Moore Corporation. It's actually pretty simple, right? You see it right here. It's simply going to be that equilibrium rate, that I star equation that you see in the text, and that I also think you're going to use for number 1, where you're simply just adding together the real interest rate, the inflation premium, the default risk premium, the liquidity risk premium, and the maturity risk premium, right? So that's really simple to do. So that gives you your 6.65%. That's not too challenging. I would not expect anyone to really have any trouble with that problem. But part A, I think, kind of requires some additional understanding to be able to know exactly why you need to use the Fisher effect for this question. So the Fisher effect, the approximation of the Fisher effect, is simply I star is equal to the real interest rate plus the inflation premium. So then the question becomes, all right, we know from the problem that the 1-year T-bill rate is 3.25%. And the real interest rate is 2.25%. So how do you know to use the 1-year T-bill rate here as I star? And here is basically the reason why. When you buy a United States Treasury bill, the only additional premium that you can ask or require to be compensated for is inflation or reductions in purchasing power, right? The U.S. T-bill market, there's no default. There is a zero default risk on the U.S. government. So there is no default risk premium. So that gets rid of that. The U.S. T-bill market is the most liquid market in the entire world. So there is no liquidity risk premium. So you can get rid of that. So this is zero. This is zero. The maturity risk premium. The maturity risk premium only really comes into play when you deal with longer term bond securities. By its very nature, a U.S. T-bill is very short term, whether it be 1 year, 180 days, 90 days, 30 days, and so on. You usually don't get shorter than 30 days in the T-bill market. So there's no maturity risk premium either for a 1-year U.S. T-bill. So that is essentially why you can simply use the Fisher effect to back out the inflation premium. If you actually read in the text, in the Fisher effect section, they talk about 1-year T-bill rates and using them in this way, but they don't really explain it the way I just explained it, in the sense that there is no default risk premium, there is no liquidity risk premium, there is no maturity risk premium. So that's kind of how you solve number 2, and I hope that's helpful for you guys. I think it is, especially going through part A. So let's scroll down here, and let's talk a little bit about number 8. So number 8 is very similar to some of the previous problems you do, like number 3, number 4, number 5. But I think 8's a little bit more involved, and so I figured we would go ahead and go through 8. It's a little bit more involved from an understanding standpoint and from a mathematical standpoint. So I think it's going to be pretty useful to go through this problem. So the question stem provides you with this information. The rate on a 4-year bond today is 5.6%, right? Like when you see subscript 1 capital R subscript 4, that subscript on the left refers to what time you're at right now. So we're at period 1, right? We're at the beginning of period 1. The subscript on the right refers to how long that investment is going to be for. So this is a 4-year bond today. This is a 5-year bond today, right? And you're given this information, 5.6%, 6.15%, okay? Now you're also given, or you're asked to find, what is the expected rate? What is the expected 1-year rate in 4 years? So 4 years from now, we will be at period 5 because we're at period 1 right now, right? So if 1 plus 4 is 5. So we'll be at period 5. What is the 1-year rate expected to be? That's why you see the capital E. What is the 1-year rate expected to be at period 5? So whenever you're dealing with expectations, you use a lowercase r, not a capital R. Capital R refers to rates that are actually spot rates today, that are actually in effect. Lowercase r typically deals with your expectations of what rates are going to be in the future. Okay, so once you have that information, that's how you get down to this equation. Okay, now this equation is very similar to the equation that you use in questions 3, 4, 5, and you see an equation like this, you kind of see the variable setup of this guy in the unbiased expectations section of the chapter, okay? And that's what you need to use to solve this problem. The unbiased expectations theory basically reminds us that whether you're buying a 5-year bond today or you buy 5 consecutive 1-year bonds, your overall return should be the same. Okay, your overall return should not be any different. And so that is kind of the premise behind how these equations set up in terms of using the spot rates, using the expectations of 1-year rates in the future, right? The idea is whether or not you buy a long-term investment today or a series of short-term investments, your overall return should not be any different. If it was any different, then you'd have an arbitrage situation, which is a riskless investment, and investors would come in quickly and take advantage of that, and then it would disappear. Okay, so that's kind of how this equation sets up. More specifically, the 5-year rate today has to be equal to 1 plus the 4-year rate today raised to the 4th power times 1 plus the expectation of the 1-year rate 5 years from today raised to the 1/5 power minus 1, right? This is just the basic equation that you see in the unbiased expectation section. So basically what this is saying is if I buy a 5-year investment today, it has to yield what a 4-year investment today would yield 4 times, because I'm going to hold that investment for years 1, 2, 3, and 4. That's why you see the exponent 4 here. Also multiplied by whatever the expectation is going to be of 1-year rates in 5 years. This overall product, taken to the 1/5 root minus 1, has to give me what a 5-year investment today would also give me. So that's how this equation sets up. So the next line down, you see all I've done here is plugged in what I know, right? I just took this information and this information from up here, plugged it in. So then down here, moving from this line to this line, I just cleared out this 1/5 power. So obviously to clear out a 1/5 power, you have to take things to the 5th exponent. So that's why you see the left-hand side here being raised to an exponent of 5. And then down here, I just do the actual math on 1.0615 raised to the 5th power. That gives you 1.34772. And then from here, it's pretty straightforward, right? Now you just simply have to divide both sides by 1.24353 and then subtract 1, and you get 8.38% as the expectation of the 1 year of what a 1-year rate is going to be 5 years from today. Okay? So that is how you solve number 8 in chapter 2. So hopefully this was helpful for you guys. And actually, wait, this is actually going to be, so 5 years from today. This is actually 4 years from today, right? So I want to make sure I was clear. When I said that, I was like, yeah, I don't think that's right. So this is let me be very clear. This is the expectation of what the 5th year rate is going to be, which is 4 years from today, right? So what is the 1 year rate going to be 4 years from today? That is the 5th year rate, right? So that's what I meant to say 45 seconds ago. So I apologize if that kind of tripped some of you guys up, but we got it squared away. We got it clarified. So those are 2 problems from chapter 2, and I hope this was helpful for you guys, and I'll see you guys next time.